Previously, we talked about a circuit, a transistor-based circuit that we could use to design a amplifier. So let's take a look at the amplifier. The amplifier we can sketch over here, and it looks like it has an output and it has an input. And we notice that we put a little signal in here, which was a variable potential, and we generated a larger signal out here. So that was the gain of the amplifier. In this case, this is an example of an analog circuit. And why is it analog? Because the input signal and the output signal can assume a wide range of values as determined by the voltage of those signals. Now, there's a whole other class of circuits that are interesting, and these are called digital circuits. So we have the world now divided in analog and in digital. And a digital circuit has digital inputs and digital outputs. So we need to change our thoughts on that. And then also it provides some function on those digital inputs in order to produce the digital outputs. So it has inputs and outputs, and it does some particular function, some predefined function. So let's go through and take a look at what is a input and what's a digital signal. And so a digital signal has an interpretation of being in a 0 value or a 1 value. Okay, and generally in most systems, not all, okay, a 0 value is when the digital signal is below a certain given potential, and a 1 value is when the signal is above a given potential. So let's take a look at this signal. We have a signal here, and this is time, and this is the potential measured in volts of that signal. Now, we can start this signal starts out here low, and then it's increasing. So during this time, this signal is interpreted as a 0 because it's below this threshold. Okay, that's pretty obvious. Now, when the signal is in this area, goes through this area, the signal is not interpreted as a 0 or a 1. The signal is interpreted as a undefined, and we generally determine that by X or don't care. So we don't know what the interpretation of the signal is through here, as indicated by when we get up above this part, because this is now the 1 threshold, as pointed out over here, the signal becomes a 1. So the signal is 1 in here. Okay, once it comes above a maximum value, the signal is no longer a valid signal. It's no longer interpreted. So it's again another don't care. Okay. Now what happens when the signal goes below now this below the maximum, between the maximum threshold is indicated here. This signal is interpreted to have a 1 value. Okay. And then it crashes through this kind of undefined zone. At this undefined zone, we really don't know what it is. And then when we go down below the 0 threshold, the signal now becomes interpreted as a 0. Now, one thing that notice is down in here, see this jog in here? This jog made no difference with our interpretation of the signal. The signal is, during this entire region through here, is still interpreted as a 0. And then we go up through this undefined area, and then we resume our the signal as a 1. So the signal is a 1 in this area. So basically what we're doing is we're quantizing or reducing the value of our signal into 2 possible values, a 0 and a 1. And just to pick up the stuff that we don't need, we also would include a don't care. So this is some logic functions we can do. So rather than talk about voltage of our signal, okay, what we're going to do is we're going to talk about now the abstract of the signal, what those signals are. So for example, I have a very simple function. This is a logic function. It has an input, as we said, a digital input, and it produces a digital output. When the digital input is 0, it's going to produce a 1. When the digital input is 1, it's going to produce a 0. So all it does is it flips everything over. We can write this as kind of an algebraic statement. So it says that the output is whatever the input is, and we're going to go through and we're going to flip it. And that's what this over bar is. So this over bar is actually, and it actually reads not. So we call that not. So we read this as the output is the input not, or the not input. We can actually write this as an abstract circuit. We would have an input here. It kind of looks like an amplifier, actually. We have an input here. We have an output here. And see this circle here? This circle is pretty universally reserved to indicate not. This is called an inverter. It basically inverts. It takes inputs and it inverts them. A 0 goes to a 1 goes to a 0. You say, what good is that? Well, just wait a moment. And then we can also have a circuit that has more than 2 inputs. So here's a digital circuit with an A input and a B input, and it produces a single output C. So what does this do? Let's see, just arbitrary, okay? When both of them are 0, C is 0. When A is 1 and A is 0, B is 1, C is 0, and so on. So we can go through and look at each row of these and say what do we do with the A-B signal pair in order to produce the output C. Now what it says here is it says that in order for C to be 1, A and B have to be 1. And that actually is exactly what we call it. We call it an AND function. And we abbreviate the AND function with the little C dot here. And normally that's reserved for multiplication in algebra, but in digital algebra, which is called Boolean algebra, we use this little dot as a way of indicating AND. So this says C is equal to A and B. Now we can also express it as a little circuit, and that circuit looks like this. Okay, this is an abstract circuit. You have an A input and a B input, and it's going to take the AND of the A and the B, and it's going to produce a C output. Okay, so we have those. And then just to kind of extend this, we could have circuits that of course have more than 2 inputs. It could have many inputs, but let's say we have just 2 inputs, A and B, and it's going to produce a output S and C, arbitrary outputs. And I just said, here's the outputs. Okay, if A and B is 0, S is 0, A is 0, B is 1, S is 1, and so on. Okay, so I can take a look at something like that. Now, that has no name, so we're just going to say it has no name. Okay, and then it has no particular symbol to it, so that would just be, we'd just use a rectangle with A and B as inputs here, and then S and C as outputs here. Now, the question is, how can we write the symbology or the Boolean expression for this? Well, I'll just take one of the outputs, and let's take a look at S. So what is S? Okay, well, S is 1 in only 2 of the rows. The first row is here, and so what we're going to say here, that it's when A is equal to 0 and B is equal to 1. So B is equal to 1 says we can do it this way. And we're looking not for A to be equal to 1, for A to be equal to 0. When A is equal to 0, what is A bar? A bar is equal to 1. So we can express this piece of the truth table into this term. Okay. Now, but that's not the only place that C is equal to that C is equal to 1, because another place C is equal to 1 is right here. So what makes that happen? Let's see. A has to be equal to 1, and B has to be equal to 0. Do you see what the bar does on it? When B is 0, B bar is 1, or not B, is 1. And so this is 1 and 1. That's a 1. So this represents that part. And then how do we put it all together? We put it all together by saying either or. So S is going to be equal to 1 when this happens, or this happens. And so we can go through and write the Boolean equation that way. Okay, let's take a look at a very simple circuit that may give us some idea on how this thing could work. The first circuit is just a couple of diodes. So I have two diodes, okay? One diode's hooked up to input A, the other diode's hooked up to input B. The diodes are connected to a resistor, and the resistor is attached to ground, okay? So let's assume when we have a 0, we have 0 volts. This would be our logic family. When we have 1, we have 5 volts. Okay, so let's see, and then anything in a 1 is anything greater than 2.5 volts. So 1 is anything is equal to any input that's greater than 2.5 volts. Okay, so that's our logic family. And similarly, a 0 is implied as anything that is less than 2.5 volts. So let's see if we can get this logic to work. Okay, so let's see. We have a 0. Okay, we first start off with this, and we assume we have a 0, 0. So if we have a 0 here and a 0 here, that implies that we have 0 volts here, and we have 0 volts here. Well, we have 0 volts for A and 0 volts for B. Neither one of these diodes is forward biased, so basically they don't exist as far as the circuit's concerned, or current does not flow. And then all we have is we have a resistor attached to ground. So that means C is equal to 0 volts, which implies that C is a 0. So what we have is we have the first term here is C is equal to 0. Okay, that's pretty straightforward. Let's go through and look at the second term. And remember, the first term was C is equal to 0. The second term is when A is equal to 0 and B is equal to 1. When A is equal to 0 and B is equal to 1, we get 0 volts on A. And then we get 5 volts on B. Well, what happens when we get 5 volts, 0 volts on A? 0 volts on A does not forward bias the diode. Okay, so there's no current that flows. When 5 volts are on B, we get a current that flows this way, because now this second diode becomes forward bias. So C ends up to be something around 4.3 volts. But 4.3 volts, because why is it 4.3? Because we have the forward diode bias drop. And so what we have here, this will go through and is a 1. So now we have a 1 here. Okay? Now, what happens if A is 1 and B is 0? Well, isn't that basically the same scenario we just did before? So that would also give us a 1. And finally, what happens if A is 1 and B is 1? Both those diodes want to be forward biased. That also gives us a 1. So this little circuit that we have over here actually goes through and it produces this truth table, which is shown here. We can abstract that truth table by going to the next slide. And this is the truth table we just did, okay? And this is saying that C is equal to A or B, okay? So that C is equal to A or B, and that's what this circuit generates. So we actually have kind of an equivalency here. We can talk about this truth table, which is the OR. We can talk about the Boolean algebra here, which is the OR. We can talk about the circuit, which produces that OR function under proper given assumptions, or we can talk about the symbol that produces the OR function. Now, let's make sure that we understand something, is that this symbol for OR has this kind of arching back in it. The symbol for AND had a straight back. And it also has come around. This is terrible. Forget that. Has a straight back, and it has a round front on it. This has an arching back, and it has more of a pointed front on this. So we have to be careful on interpreting these to make sure we understand the symbology. But this is an OR function, okay? So we can actually talk about AND functions and OR functions. We talk about inverters. We can actually now have some understanding of the kind of circuitry necessary to make this happen. And by the way, nobody uses diode logic except for some of the most ridiculously simple problems. But this was just posed as a way of understanding how these things could be built. Okay, so here's what a real OR gate looks like. Okay, this is called a SN7432. Okay, it's a TTL. This is transistor logic, no diode logic, no diode resistor logic. And we talked about before, this is A is equal to A or B, or C is equal to A or B. This is the truth table for it. This is the symbol for it. And this is actually the circuit diagram for it. Okay, and we're not going to crawl through the circuit diagram. I just wanted to point out that the input A is here, the input B is here, and it's kind of interesting. These inputs are applied to an emitter here in this, and that's what makes it transistor TTL, transistor logic. Okay, these are just diodes that are called clamp diodes that prevent this thing from that basically prevent the inputs from damaging the transistors, and the output is produced here. Okay, and this output looks like it has two transistors. This has a transistor that looks like it's trying to source current, and this has a transistor that looks like it's trying to sink current. And there's a whole bunch of junk in here that determines which one of these two transistors are turned on. So this is a real circuit. We won't be designing them because we're going to be buying them and using them in packages. Okay, so let's do something very quick, and let's see if we, actually this would probably be a good place to stop. I'm going to stop this video right now.